There are a lot of fundamental identities that you need to have memorized. Now, actually, a lot of these you already have memorized, a lot of the ones that are on the paper, as we've been doing them in little bits and pieces to make them a little bit easier to handle. So looking through the ones that we have here, these reciprocal identities, those should be like second nature to you by now. So I'll move down the screen just a little bit here. Quotient identities, those you also should know. Tangent is sine over cosine and cotangent is cosine over sine. The Pythagorean identities, I told you if you know this one for sure, the the fundamental one, then the other two are just a result of manipulating that one. So sine squared plus cosine squared equals 1. It is helpful, though, to know the other two. You'll be a little bit quicker and be able to see things faster. So 1 plus tangent squared is secant squared, and 1 plus cotangent squared is cosecant squared. And that brings us down to our new ones here. Oops. So our new ones are these co-function identities. Co-function, if you notice the names of the trig functions that we've been working with, we've got sine and we've got cosine. Cosine is considered the co-function for sine. And that means that essentially it's the same function, except it's translated pi over 2 to the right. So for our co-function identities, you'll notice there's something similar with all of these. We've got a pi over 2 minus u inside the parentheses after one of the trig functions there. So if you've got sine of pi over 2 minus u anywhere, that can be rewritten as cosine of u, and vice versa. So cosine of pi over 2 minus u is equivalent to sine of u. Cosecant and secant are co-functions also, so they have the same relationship. And cotangent and tangent are co-functions, so they have the same relationship also. So anytime you see within one of the problems that you're working with a pi over 2 minus u, or pi over 2 minus theta, or pi over 2 minus x, you should be thinking about these co-functions. The last identities that we have that we're going to be working with right now are the even and odd identities. These have to do with the relationships on the graph. Now, the functions that are considered odd functions are these four over here, which is why I have them organized this way. With odd functions, if you've got that function of a negative angle measure, like sine of negative u, sine of negative theta, that negative sign could be brought to the front of the trig function and taken off of the argument of it, and it is equivalent. So that kind of gets the negative out of the angle area and makes things easier to deal with there. So for our odd functions, we've got sine, cosecant, tangent, and cotangent. So with all of those, if you've got that trig function of a negative angle, you can bring the negative to the front of the trig function. Now for the two even functions, there are only two that are even, and that would be cosine and secant. Now with cosine and secant, if you've got cosine of a negative angle, or secant of a negative angle, that's equivalent to cosine of just the positive angle, or secant of the positive angle. So essentially with that, it's saying if you've got a negative in there, you can pretend like it wasn't there at all. And again, that'll make things a little bit easier to deal with. Okay, so what we're going to be doing today, our goal, is to use these trigonometric identities to rewrite an expression in terms of another expression. Now, you do have to have those trigonometric identities memorized. If they aren't in your head, you're going to have a hard time seeing them, seeing what you can do. So the more familiar you are with them and the stronger your understanding is of those, the better you're going to be at manipulating these trig expressions here. So we're going to start with this first one over here. The directions tell us to simplify each trigonometric expression. So our first one over here says we've got cosine of beta times tangent of beta. To simplify that, I'm going to be thinking about ways that I can replace either cosine or tangent. And I'm going to try doing just one thing at a time. So first thing that occurs to me is that I could rewrite tangent with a cosine in it using the quotient identities. So tangent is the same as sine over cosine. So I could rewrite this as sine of beta over cosine of beta. Now, once I've written it like that, then I can see that there is a relationship there that now I could use just what I know about basic mathematics. Cosine of beta divided by cosine of beta will cancel out. So that's going to give me just sine of beta. And so this would be a simplified expression, and it's equivalent to the original. What's interesting about that is that in the original, sine didn't appear at all, but it is in fact equivalent to cosine of beta, tangent of beta. Okay, for our second one, we've got secant squared of alpha times the quantity 1 minus sine squared of alpha. Okay, so once again, I want to simplify this using those trigonometric identities at the top there. Now, whenever I see a trig function squared, I start thinking about the Pythagorean identities, particularly when it's got something where it's like 1 plus that or 1 minus that, or maybe two trig functions squared added together or subtracted. So I think I'm going to focus on this inside part here first. That 1 minus sine squared of alpha. That one sounds to me, this is going to be a little aside, so this is not actually part of the work here. It sounds to me like sine squared alpha plus cosine squared alpha equals 1. That original Pythagorean identity. Now, if I manipulate this one just a little bit, I can make it look like that one. So if I were to subtract sine squared of alpha once from each side of this equation, this identity, then it would say cosine squared of alpha is equal to 1 minus sine squared of alpha. Oops. So that means I could take this 1 minus sine squared of alpha and I could replace it with cosine squared of alpha. So that's going to be my first step here, the first actual step for this problem. So this part here was just an aside, just an explanation. And I'm going to replace that 1 minus sine squared of alpha with cosine squared of alpha. All right, now I'm seeing the two trig functions that are in there are secant and cosine. Now, there is a relationship between secant and cosine also. They do both say squared, but there's no pluses or minuses going on in either of those now. So I'm thinking probably Pythagorean identities is not the way to go. But I know that secant and cosine are reciprocals of each other. So to simplify this a little further, I think I'll replace secant squared of alpha with 1 over cosine squared of alpha. And once I have it like that, again, I can use what I know about basic mathematics. The cosine squared of alpha being divided over here and being multiplied there will cancel out. And so that leaves me just with 1. So that's really interesting. That means this very complicated looking thing that we started with is actually just equivalent to a 1. All right, for our next example, we've got secant of phi over cosecant of phi. I'm using a lot of different Greek letters here just to kind of expose you to them. This one is phi. Okay, so once again, I've got secant and cosecant. I'm trying to simplify this, so I'm thinking about ways that I can replace secant and cosecant. A nice thing to fall back on if nothing else is really coming to mind. Like I'm thinking secant and cosecant, the only relationship that I had for them was the cofunction identities, but I'm not seeing a pi over 2 minus something as the argument for either of these, so that's probably not the right way to go. So I think I'm just going to change everything into sines and cosines and see where that takes me. So for secant of phi, secant's reciprocal would be 1 over cosine. And cosecant of phi, the reciprocal function for cosecant is sine, so that would be 1 over sine of phi. And so now I've got this compound fraction to deal with here. Now for the compound fraction, I'm going to treat this like it's a division sign, because it is. And then it just becomes dividing fractions, which is handled by multiplying by the reciprocal of the second one. So now if I were to multiply these together, multiplying fractions, you just go straight across. So I would say sine of phi over cosine of phi. And now I could go a little bit further because sine over cosine is the same as tangent. So this would be tangent of phi. So this would be my simplified version of that one. Again, really interesting. Nowhere in the original problem was there a tangent, but it is in fact equivalent to tangent. Okay, so for our next example over here, maybe you're feeling a little confident about these now, and you want to try that one. So you could pause the video here and see if you could figure out how to simplify that one. Now, one thing to note is you may not take the same path that I do here on the video, but we should end up with the same result. So let's see, I've got tangent squared of x over secant squared of x. I'm thinking to myself, well, I'm seeing a trig function squared, so there's a possibility I could be thinking about Pythagorean identities. If I didn't want to try that, I could be thinking about maybe doing changing everything into sines and cosines and see where that takes me. Either one of those would be a good place to start. So I think I'm going to do this one with the Pythagorean identities. Now, fractions are easier to work with if the denominator is composed of a single term, so no pluses or minuses. So I'm going to leave the denominator alone on this one. And for the numerator, I'm going to change that tangent squared of x into what is equivalent to, using the Pythagorean identity. So let's play with that a little bit. This tangent squared of x plus 1 is equal to secant squared of x. And so if I wanted to get tangent squared of x by itself, I would need to subtract 1 from each side. So that would give me tangent squared of x is equivalent to secant squared of x minus 1. So now for this numerator, I can replace it with secant squared of x minus 1. Now, like I mentioned before, it's easy to work with a fraction when the denominator is a single term. With your denominator as a single term, you can actually split up your fraction with each term of the numerator over the denominator separately. Now, if you take a moment and just think about that, if you were subtracting these two fractions, you would keep the denominator the same and then just do whatever it says with the numerator. So you should be able to convince yourself that this is equivalent to that. All right, so now I can look at each of these fractions and see what I can do to simplify there. So secant squared of x over secant squared of x. Anything divided by itself, of course, is 1. And 1 over secant squared of x, well, 1 over secant is the same as cosine. So 1 over secant squared would just be the same as cosine squared. And this is now looking very different from what I started with. Now it says 1 minus cosine squared. And I recognize that that actually is closely related to one of my other Pythagorean identities. 1 minus cosine squared is the same as sine squared. So now I could replace that with sine squared of x. That would be about as simple as I could make this one. Now you could also try this one with changing everything into sines and cosines and see where that takes you. That's also a very interesting exercise. Something I really like about these problems is that you can do them several times and the experience is very rich each time. You can do something different and still end up in the same place. Okay, so for our next one here, we've got cotangent of pi over 2 minus theta times cosine of theta. Now within this one, I'm seeing pi over 2 minus theta. And so immediately I'm starting to think about cofunction identities. So the function that has that as its argument is cotangent. So the cofunction for cotangent is tangent. So that means I could rewrite this just as tangent of theta times cosine of theta. Once I've done that, I'm thinking, well, probably writing things in terms of sines and cosines would be helpful here. So I'm going to rewrite tangent of theta as sine of theta over cosine of theta. Oops, not equals, times. Okay, and then again, once I've done that, then I can use what I know about mathematics there. Dividing by cosine and multiplying by cosine cancels out. So that leaves me with just sine of theta. And once again, a very interesting result. Looking at the original problem there, I probably wouldn't have guessed that that was equivalent to sine of theta. All right, for my last one over here, 1 over cotangent squared of y plus 1. Well, looking at the denominator of that one, I see cotangent squared of something plus 1. So cotangent squared, that's going to be one of my Pythagorean identities probably. So I think my first move would be to replace that. So if I go back and look at those Pythagorean identities, cotangent squared of y plus 1, or 1 plus cotangent squared of y, would be equivalent to cosecant squared of y. So that gives me 1 over cosecant squared of y. Now 1 over cosecant of y is the reciprocal identity for sine of y. So 1 over cosecant squared of y would be sine squared of y. And that would be about as simple as I could make that one. So again, really interesting result there. There's probably another way or several ways that you could get to that result. Again, it's kind of fun to play with these and try doing them several different ways and see what you can get as an answer. Okay, so to practice these, keeping in mind that you're trying to memorize these identities, You're going to be working in the textbook, pages 354 through 355, numbers 21 to 32, and 33 to 43, odd only. So only do 33, 35, 37, 39, 41, and 43 there. I will attach a PDF of that along with the assignment for this one.